Within the Maths A level, there are two types of sequences you'll want to be familiar with, one of which is the arithmetic sequence. Now what we mean by this is that if you were to have a series of numbers, you would find that to get from one term to the next, you're either always adding the same number or minusing the same number. So you're going up in intervals of 6 maybe, so add 6 each time, or -1, you're taking 1 away each time. In order to find a specific term within this series, this sequence, to get the nth term, you would be using the formula a plus, in brackets, n minus 1, close bracket, times d, where a is the first term in the sequence, n is the place in that term, so if you were after the third term, you do n is 3, and then the common difference here, just what are you going up in? So let's say we had a sequence which was 17, 21, 25, 29, and you want to know what the fifth term is. Well, we can see here that you're going up in intervals of +4, you're adding 4 each time. So in order to just get the next term, we could just do +4 again, and you'd end up with 33. However, if for this sequence you would rather get the 50th term, not just the 5th term, well, our A is this 17, we started at 17, then plus 50 minus 1, and you times this by your common difference of 4. So you just put into a calculator, 17 plus 50 minus 1 is 49, times that by 4. You get a 50th term of 213. As well as getting a specific term, we can also then get the sum of however many terms. So Sn here just represents the sum of, well, if it was the first 50 terms again, it would be S50, 5, S5. For this, we're going to have n divided by 2, and then open bracket, 2a add n minus 1d. So you'll notice here the a plus n minus 1d is the same formula as we were just using for your regular nth term. We've then just got these extra bits surrounding it. Now, before we get into any actual questions which will involve you working out either an nth term or a sum based on some terms they already give you, I'm actually just going to go through the proof of why this is the case in the first place, because that is just as much a valid question that could come up in a paper. They ask you to prove the sum of an arithmetic sequence. Well, if instead of just writing the sum like this, we instead say that you'd have your first term of just a, and adding to that you'd have your second term. Now, the second term will be a with d added to it, because that's you're adding on the common difference. Then you'd add your third term, which would be again that a, but now you would have added 2 lots of the difference. And so on and so forth, until you have like a plus n minus 2d plus a plus n minus 1d. Now the reason for this at the end is rather than it just being nd, is you're going to have 1 fewer n than the given term place. So here, in the first term, you had 0 d's. In the second term, you had 1d, third term, 2d. So for the nth term, the final term, because it's a sum of n, you'd have n minus 1d. Now, because it's addition, we could actually write this sum going the other way round. So we could say that it's a add n minus 1d plus a plus n minus 2d plus a plus n minus 3d, going all the way to a plus d plus a. So it's the exact same sum value because it's the exact same terms all added up. It's just you added them in the reverse order. Now what you can do with this is say if you were to then add these two sum equations together to get two lots of the sum of n terms. This a here you could think of as being added to the phrase a plus n minus 1d. So algebraically you'd have 2a plus n minus 1d. Then this a plus d is going to be added to the a plus n minus 2d because they're both the next terms along in each sequence. A add a is going to give you 2a, and then d add n minus 2d is going to give you n minus 1d because you have one more d than you did before. And so forth, all the way to the end where this a plus n minus 1d is added to your final a, again giving you 2a plus n minus 1d. Here, therefore, for every single term in the sequence, you end up with a phrase of 2a plus n minus 1d. Therefore, you can say that's simply n lots of that phrase. With that in mind then, if that's just two lots of the sum, a singular lot of the sum, if you divide by the 2, this becomes n over 2, and then that same bracket again. There you go, that is your proof. If the question yet therefore asks, prove that that is the sum, you would just give these 4 lines, just parrot them back, and that will get you the marks. With that then, let's actually get on to a question that involves plugging in some numbers somewhere. So up here, we're told that the 15th term of an arithmetic sequence is 34. The sum of the first 19 terms is 456. Find a and d, and then when you've done that, find the values of n for which the sum is greater than or equal to 650. To deal with the first part of the question, finding your a and your d, well, to have some a and d's, we need some expressions that contain them. If the 15th term of the arithmetic sequence is 34, we're saying that your a term, whatever that is, added to 15 minus 1d, that equals 34. So if you want, we can, so a plus 14d. As for the second sentence, we're saying the sum is 456, so we'll have 19, which is your n, over 2, then brackets 2 lots of your a, plus 19 minus 1, d equals 456. If at this stage we just wanted to simplify, we can say that 15 minus the 1, that's going to leave you with 14d, and here 19 over 2 times by 2a, well, they divide by 2 times by 2, they're going to cancel, leaving you with just 19a, and here the 19 minus 1 is going to give you 18, and then the 19 over 2 times by 18, that's going to give you instead 171d equals this. At this stage, what we have is two equations, both involving a and d, and they equal different things. These are going to be simultaneous equations. How we deal with simultaneous equations is to make one of the letters have the same coefficient in both equations. We cannot solve while there are two unknowns, so we want to get to a stage where we can eliminate. Let's say we're making the a the same. The easiest way to make the a the same is to make this 19a to match this 19a. So what we're going to do is times by 19, but if you times one thing by a value, you have to times everything by that value. So 14 gets times by your 19 as well, to give you now 266d, and 34 is going to be times by the 19 to give you 646. Now that these a's are the same, what we can do is take the equations away from each other. So if the signs in front of these coefficients are the same, you'll take away. If it was a plus and a plus, you'd minus. If it was a minus and a minus, you'd minus. Because in both cases, you're taking away itself, that makes it disappear. If one was a plus and one was a minus, however, you would add the equations. So if it was a positive 19 here and a negative 19 already here, you'd add them to get to cancel. Either way, if you can get the signs the same, you minus the second equation away from the first equation. So 19a minus 19a is nothing. 266 minus 171, that leaves you with 95d. And then here, 646 minus 456, that leaves you with 190. So 95d equals 190. D therefore equals 190 minus the 95, divided by the 95, which gives you a common difference of 2. Now that we know this 2, we can plug it back into whatever equation we want. I'm actually going to rewrite what we had previously up there, which is a plus 14d equals 34. So d, as we now know, is 2. So 14 times 2, which is 28. So a plus 28 equals 34. A equals 34 minus 28, which is going to be 6. So we now know our a is 6 and our d is 2. We would have got the same values if we'd made the d's the same previously as well. Now that we know these, we can move on to the next part of the question, working out for what range of values Sn is going to be greater than or equal to 650. So I'll just keep these a and d's here for a second so we have a record of them. Your Sn is going to have that equation from before of n over 2, but now I know it's 2 times 6 for the a plus n minus 1, and then d we know is 2, and we're looking for this to be, say, greater than or equal to 650. Well, expanding here, just kind of like we had in the previous part, n over 2 times by a 2, the divide by 2 and times by 2 are going to cancel. So you essentially just have your n times 6, or 6n. Here, you would have 2 times n and 2 times minus 1, so 2n minus 2. Timesing this by n over 2, though, you're going to end up with n squared minus n. So again, just to be clear with that, so you have your n over 2 times by 2n minus 2 here. So that coming from here, and that then gives us that. This again is greater than or equal to 650. Okay, so now that we have this, we can remove these. And simplifying slightly, you end up with n squared. This is then going to be plus 5n. Now, if I bring this onto the same side, this will become minus 650. That's going to be greater than or equal to 0. Now, this is a quadratic equation. You have some letter squared plus an amount of that same letter plus or minus a number is compared to 0. If we're solving a quadratic, we can either break it down into 2 brackets or use the quadratic formula. In this case, because we don't know if it's going to go nicely, I mean, if we don't know the factors of 650, assuming it works anyway, let's just use the quadratic formula. So this thing where if you have like a lots of x squared plus b lots of x plus c equals 0, you can plug that into minus b plus or minus square root b squared minus 4ac over 2a, and that will give you the x value for which this is true. Here, our b, the numbers in front of the middle term, is 5. Our a is 1 because there's one lot of n squared, and our c is the minus 650. You have to include the minus in this sort of thing. So if we say, so minus b, minus 5, plus or minus, this just means we're going to do it once when it's a plus, then do it again when it's a minus to get a second answer. The square root of 5 squared minus 4 times 1 times minus 650. That's all over 2 times 1. One way, if say one decimal place, we get n equaling 23.1. The other way, you get minus 28.1. Now, this isn't actually equal 0 like the quadratic formula equation here. This is greater than or equal to 0. In general, with inequalities and quadratic inequalities, if we're not sure as to whether our n value actually lies between these numbers or on the outsides, what you can do is just try to do a rough sketch. So here, this is a positive quadratic, so they form a positive parabola, which is like a U shape cutting through the axes here. This point here is the minus 28.1. This point here is the 23.1. Now, if we're looking for when this curve is greater than or equal to 0, that's happening either up here or down here. It's on the outsides of the value. But not only that, because of this, we can say that n just has to be greater than or equal to 23.1, because we cannot have a negative n value. You can't have a minus 28th place in a sequence. The smallest value n can take is 1 for the first term. And in turn, because n has to be a whole number, you can't only have not only have a negative n term, you can't have a decimal term, because you can't have like half a term in a sequence. If n is greater than or equal to 23.1, what we're really saying here then is n is greater than or equal to 24. So this here is the range of values for which the sum will be greater than 650 if there are 24 or more terms. Okay. If we're all right with this, let's just see what an exam-style question may be. Here we're told that the second, third and fourth terms of an arithmetic sequence are 2k, 5k minus 10 and 7k minus 14 respectively, where k is a constant. Now show that the sum of the first n terms of the sequence is a square number. So what we see here is that in an exam paper, they can also not only throw at you the topic of arithmetic sequences, but they can throw in more unknowns. We know even less about the A and the D because they in turn have some algebraic letters within them rather than being fixed values already. And not only this again, but the question also ties us into the topic of proof. We have to show something, or rather, it's rather common within proof, show it's a square number. So, what we can say is that because we know that 2k is the second term, that a plus 2 minus 1d will give us our 2k, a plus 3 minus 1d gives us the 5k minus 10, and a plus 4 minus 1d gives us 7k minus 14. Now, once again, we're in a kind of situation which is sort of like simultaneous equations, but this time we have 3 unknowns, as has already been stated. So we're going to have to treat this slightly differently. We can still start by trying to take equations away from each other. So let's just say if we label these equation 1, equation 2, equation 3. If we were to do that equation 2 minus equation 1, we would have, so a plus, now 3 minus 1 is 2, so a plus 2d minus a plus d, because 2 minus 1 is 1. So here a minus a is going to be nothing, 2d minus d is d. On the other side of the equals sign, you end up with 5k minus 10 minus 2k. Well, 5k minus 2k is 3k, and then that's just minus 10. So d is 3k minus 10. If separately we were to do our equation 3 minus our equation 2, you'll end up with your a plus, now this will be a 3d minus a plus 2d from 4. So a minus a again disappears. 3d minus 2d again just leaves us with a singular d. And on the right hand side you have 7k minus 14 minus the 5k minus 10. 7k minus 5k is 2k, minus 14 minus minus 10. Minus of a minus becomes a plus, so minus 14 add 10 leaves us with minus 4. Now what we can do at this point, because both of these expressions are equal to d, which makes sense because there's going to be a common difference between these terms, is that 3k minus 10 has the same value as 2k minus 4. Here we can just solve algebraically. So if we bring the k's onto the same side and non-k's on the same side, this gets us 3k minus 2k on the left, because when you move something over the equals sign, its personal sign changes. It was a positive here, so it's now a negative. And on the right-hand side, the minus 4 stays minus 4 because it was already there, it hasn't moved. But the 10, that's now becoming a positive 10 because it was a minus over here. Again, the sign changes. Simplifying, 3k minus 2k is just a singular k, and minus 4 add 10 gives us 6. So we know that k is 6. With this information, we can now get d, and once we have d, we can get a. So d equals 2 lots of the 6 minus 4. 2 times 6 is 12, so 12 minus 4, that gives us a common difference of 8. And plugging this value, say, back into the first equation, you had a plus, remember, so the 2 minus 1 is just 1, so 1 lot of d, 1 lot of the 8, equals 2 lots, and the k was 6, so it'll be 12. So a plus 8 equals 12. So a is 12 minus 8, which gives us a first term of 4. Now that we know our a and our d, we can get the sum of the first n terms. So our sum of n is going to be n over 2 again, because we're trying to prove it for any value of n, so we're not going to put a number in here, we're going to keep it as n. We'll say 2 lots of the 4, which was our a, plus n minus 1, and the d was 8. Well, from this, simplifying, 2 times 4 is 8. This will then be plus 8n minus 8. From here then, well, 8 minus 8 cancels, leaving us with just n over 2 lots of 8n. Times them together, you get a sum of, so 8 divided by 2 is going to be 4. N times n is n squared. I can see here from the square that it is a squared term, but just to absolutely show it, we want to say that that's the same as 2n all squared. So whatever n is, the sum total gets squared. It must be a square number.